Okay, so we're looking at the so-called conservation equations now, and this is my attempt to develop a theoretical framework from the very basics of calculus even. So far, the way that we've developed our equations of conservation for mass and written in terms of moles and so on has been by looking at particular case studies, looking at the momentum, the molar flux, and adding that up over control volumes and so on. So this is, in a sense, an alternative approach to that, and it uses some calculus that is really covered, I think, in your third year of study. So we will, some of these things we will describe more intuitively than anything else. And in a sense, this section is optional because it is an alternate view of doing similar things to what we've been doing so far. But I think it does give some insight. And when you do reach these topics in maths, then I think it does help to give more context and so on. So it starts all the way from your very most fundamental theorem of calculus, where the statement that if you want the difference in the value of a function at in one specific region and another specific region, so the difference in the function value, so basically this distance here, if you want this distance, you can get that by integrating along the line. So here's the integral. You are taking the derivative along the line and you are adding up all the changes, and that gives you the overall change. So if you read this equation, not in the strict formal sense, but if you read it, if you look at what it actually means, it's saying the changes along the line, if you add up all the changes along the line, it gives you the overall change. So that's another way to read the fundamental theorem of calculus, right? And I think it's useful to start looking at these things, not kind of in their most strict sense as, you know, or not strict, but in the purely formal sense about, you know, the meaning of a derivative and so on. If you can kind of feel this equation in terms of, oh, this is just talking about changes along a line added up all across a certain range here, then it starts to make much more sense. So that's your fundamental theorem of calculus. And then the divergence theorem, which is typically presented in maths as a purely independent thing, this is actually nothing but the same. This is, in a sense, the line version of this, which is the volume and area version. And if you think about this equation, it's this is an integral along a line, and this is a difference between points, right? And if you think of the dimensional changes, right? You go, a point is the starting, I don't want to say point, but the point, a zero-dimensional space is the start. Then a one-dimensional space is a line. A two-dimensional space is a surface. A three-dimensional space is a volume, and so on. And you can extend it to hyper dimensions, a fourth and so on dimensions, right? So anyway, this is the 0 and 1 dimensional area or the 0 or 1 dimensional view of the fundamental theorem of calculus. And if you look at what this is giving us, the integral over the area of a function, right? So the integral over the area, the change over between over a certain region of a function is equal to the changes of the function over the volume. Or another way to look at it is all the changes happening inside the volume of the space is equal to the changes if you just count all the changes on the surface of that space. So the divergence theorem is the statement which can be viewed as the 2 and 3 dimensional version of the same 0 and 1 dimensional version of the fundamental theorem of calculus. So if you take that view, and then if you take a more regular geometry, So if you take rectangular geometry instead of this kind of lump of coal type of volume, then you can write the changes of some arbitrary field. So the field could be, for example, the concentration or the mole fraction. So you can imagine if you pick any point in a 3D space, you can define a mole fraction there. So you can estimate the change across any two areas. So if you pick A1 and A2 being any two of those, then you can estimate that change by integrating on the surfaces. So if, for instance, and I think there's supposed to be a minus sign here, there's an error there, that's supposed to be a minus sign. But if you add up on area 1, so let's say we were taking, let's say we were taking flow in at this face. Well, let's see what C, D, E, and F, C, D, E, and F. So it's this face here, right? The one that's hidden behind the block. So this space, and if you take your function and the derivative of the function in the x direction. So here we are trying to take our function, and so our field function. So for example, if it's a concentration or something like that, so then the x doesn't matter, it's just the concentration. And then we are looking at the concentration at the specific x value of A. So here's x in this direction. And then the where x equals A, that specifies this specific plane. And then if we add up all the changes in the y and z directions, that means we are adding up over that whole interface. And then we are subtracting from all the changes on this other face there, then that's the contribution to the changes in the x direction. And so that, in a sense, starts to show us how we can add and subtract across the faces of some arbitrary volume. And so, again, if you apply your fundamental theorem of calculus, write it a bit more generally, that we are just looking at changes across areas, and then that gives us the changes across a whole volume. Then we start to see that the rest of it is just about relating those differences. So those changes across the area, we are just relating that to changes across the volume. So if you add all that together, you can simplify it using this divergence operator. So the divergence is the derivative in all directions of the vector of the derivatives of your arbitrary function, and then that gives us the this nice formula. So that's the divergence theorem. So when we apply that to mass transfer, if you think about concentration as the field, so as we said just now, we want to look at concentration as the field, and quite often we want to know what's the rate of change of the moles in that space. So we know the number of moles in the space is the integral of the concentration in the space. So ddt of that, now using the divergence theorem, it can be written like this. So if we want the integral over the volume, we can get that from the divergence of the concentration across that volume. So right now we haven't applied the divergence theorem as yet. This is just an expansion of the left-hand side. It's just saying that if we expand out with respect to volume here, then in each direction x, y, z, we can write it like this. And then here here's where we are actually applying the divergence. No, wait, this is just expanding using differentiation. So here we are saying, if we want the derivative of the number of moles, so if we want the derivative of this integral, then we can get that also by the integral of the derivatives. So you can do this if your endpoints are fixed. If you have A, B, C, D, E, F, if those boundaries are not changing in time, then this is the right formula. There is another formula, the Leibniz rule for differentiation, if your boundaries are also moving in time, but in our case, the boundaries are not moving. So the derivative of concentration with respect to all these variables, of course, we are familiar with having dc dt, but also what if x is changing? What if we are talking about moving entities as well? Then dc dt should be written as dicx, dic dx, and then dx dt. And so all of these apply as well. And what do we mean by dx dt? Well, that refers to the rate of change of property x of our species. So dx dt, that's nothing but our velocity in the x direction. So dx dt is ux, dy dt is uy, dz dt is uz, and so on. So we can talk about a vector of velocities that have been multiplied by a vector of concentration gradients. So we can rewrite all this as dic dx, dic dy, dic dz dot multiplied by ux, ui, uz. Okay, and so that gives us the nice Dell view of things. That's basically what we are writing here. So dic dx, dic dy, dic dz, that's the divergence of a scalar field. So that's shown there. And so, of course, if we dot multiply it, then as we said just now, we get back that. Okay, so all of that is saying the same stuff, right? So it's the divergence of C dot U. So that's what we have there. And then now if you go back to what we said originally, we've now represented this differentiation more compactly using this divergence form. And now if we take this across, so if you take this into the derivative, into the integral, and you are integrating on the same volume, this is integral in volume dv, so you can take this inside that integral. This is also an integral in the volume dv. So you can just take this across, or I can say what we actually do is take this one across into there, into the left-hand side. So it's d dt of c minus dic dt minus the divergence of cu. So that's the formula that we have now. And this integral is equal to a 0, right? And this is also telling us that this integral is always equal to 0. And if you think about the volume that we chose, we never specified what these boundaries are. So maybe a way to view this is if you have a function, so you've got some arbitrary function here, and we are interested in the area under the function, and then we pick a boundary. So let's say we pick this area to integrate under. So we say, I want to know the area under this, in this range. So I integrate it and I get this area. And then I say, well, this is equal to 0. So there's, so then we have to think, well, under what conditions could this equal 0? What can we say about this function for this to equal 0? Well, number one, we could say, then maybe the function is not the way it was first drawn here. Maybe your function goes negative and positive across that range. So maybe your function actually looks like this, and we don't know what happens here, but at least in this range, over the range that we are interested in integrating it, maybe the function looks like this, so that the negative parts cancel with the positive parts. So if the function is like that, so this is one possibility, that the function does this so that the area equals 0. So that's one possible case. The other possible case is that the function is 0 everywhere in the space. So if it is 0 everywhere, then the integral under it will be 0 as well. So that's the other possibility. Now, this integral is zero no matter what volume we pick, no matter what limits we pick here. So for this to always be zero, right, that means if we pick any other boundary, so let's say we keep the endpoint the same, but now we integrate a bit past that. So if we integrate past that, then there's this extra piece we have to add to our integral. And so our integral will become negative and it won't be zero anymore. So that means it's not the case that this this boundary, this function can be that the integral can be zero because the function looks like this, right? For us to always get zero, no matter what volume we choose, it must be the case that the function itself is always zero. So the function is always zero. So if the function is always zero, then that means this inner kernel must always be a zero. So that's what we write here. And then if we just move the dc dt to one side and move the rest to the other side, then the equation looks like that. If there are no explicit time changes in concentration, then we can set that out to a zero. And then, or we can recognize that there might be an explicit generation of something with time. So that's the other, so you could say dc dt, if you are explicitly adding material, then you can show that up as a generating function. So this is now the statement that we are more familiar with in chemical engineering, right? That there is a velocity, so this is like a convection term, that our species are moving around the space due to convection, and there might be generation like due to the reaction terms we had before and so on. So that is a balance that looks more like the chemical engineering we know. And then if you see, why are we doing this part now? Just a second. So yeah, if you then take a sub-volume that you integrate this over, so if you take some sub-volume delta V and you integrate left and right-hand sides over that volume, then you can convert that into then you can see that you obtain the divergence theorem there. In other words, you are starting to get what we wrote for the control volumes. So let's say we took a control volume, delta X, delta Y, delta Z. So it's a very small volume, right? This delta Z, that's a very small volume. So this integral can be approximated as this volume just times this dc dz. And then on the right-hand side, we are still maintaining the calculation for that precisely as the integral in this way, and then this generation term. Now this, we said by the divergence theorem, could be written instead as the integral with respect to area of not the divergence, but the function itself, cu. And then we've got the generation term. And then if we divide both sides by delta x, delta y, delta z, then we are getting this form. And that looks exactly like what we had before, right? So, because if you take your change with respect to the area integrated over the space, then that's the same as saying what's the flow in on one side and what's the flow on the other side, right? Looking in the x direction only, we are saying the area is delta y, delta z, and then the positions are at x and x plus delta x. So this is the same as when we derive these equations from, if you like, from the bottom up instead of from the top down. Right, so at the moment we are going from the top down. We are just integrating everything and then taking sub-volumes on top of that. So now if you apply that, then you can see we've got the same form that we are familiar with from before. Okay, and then this part, the C times UX, we recognize that as the total molar flux. And so the total molar flux is, of course, the result of bulk movement or convection and diffusion. So if we write that as ddx of CUX, sorry, ddx of CUX here, then we'll get ddx of this times this, and then we get exactly the equations that we have been getting so far. So this is this whole thing, as I said, this is all optional. You can, and this uses maths that hasn't formally been covered as yet. So it may well be that you've already learned this elsewhere, but at least in the curriculum, this is not covered as yet. But you can look at this as an alternate way to prove that you will get equations of this form if you do the derivations that we've been doing. Okay, and so that is now something that we can rewrite in this form. So we've learned about the Dell operator here, and I will show the Dell operator in a slightly different way just now, but this is another way to look at our the same equations. So this equation is written purely in terms of x, right? We just ignored changes in the y and z directions just for simplicity. There was no real reason to do it, other than we just wanted to, we didn't want to think about the other two directions also. But generally speaking, we should. So we saw now we've got this, this Dell operator, which lets us consider changes in all dimensions. So now we have a nice compact form of the equation that we are familiar with. Okay, and yeah, that's basically what the section is about. So conservation equations, we can start to see a simpler way, well, an alternate way of developing the equations that we are familiar with. Any questions or comments on that? Okay, then I'm just going to break the video here and